Okay. Full screen. Okay, so we start. This is the right pen at work. Chemical kinetics, and as you already know from earlier statements, chemical kinetics is defined as the study of rates of reaction, and so that would essentially be the first big picture topic and how we evaluate a reaction in the laboratory and its speed and so forth. After that, we will cover chemical equilibrium, which is the study of extent of a chemical reaction. How long or how far or to what extent will it take to reach the equilibrium point for a given process? And then finally, we'll end our major topic session on studying reactions with thermodynamics, which is actually defines the feasibility of the reaction. So these are major several chapter concepts, especially the equilibrium. The equilibrium will have divided into gas phase equilibrium, liquid phase, and solid liquid phase interface equilibriums. And you'll see how that applies to the big picture of studying reactions. So as we start this, we want to define the nature of chemical kinetics. Kinetics, in essence, is rate. Rate in itself is a change per unit time. If you're talking about the speed at which a car travels, you would define its rate in terms of change in distance per unit time. In chemistry, we use terms like concentration changes per unit time. So rate in the concept of rate is a change in concentration over a period of time, or a change in time. Now, we evaluate this in terms of concentration because this is something we can measure using various instruments. And the essence of this can be shown, and I think I put this up for your benefit in the last class, as a function of time and concentration. We find that a given reaction, going from reactants going to product, starts 100% reactant and 0% products as we start a reaction. Now, again, and I'll repeat this many times, when we talk about a reaction in the kinetic region, we want to put that reaction in a starting gate, much like a horse race. And when you do, you haven't produced any products at all. So it's 100% reactants. So as we're at time equals 0, we're at this particular point. So then we open the gates and let the reaction run, so to speak. A and B start reacting. Well, once you start forming A and B in the reaction of products, the concentrations of the reactants will certainly drop down and the concentration of products will increase. And let's look at this as a individual, a single component reaction. One component, A, starts breaking down or does whatever it does and changes to whatever it changes to. It doesn't matter. But in essence, you will see the concentration, of course, drop, and at some point level off. The concentrations of products will follow the same procedure, but they will level off at a higher concentration, like that. At the point where these level off, or take zero slope, and the contact is the end of the kinetic region. And beyond this point is the equilibrium region. And so what we're studying right now is within this little bracket right here. And the reason it is a study of rates is that if you took any one point in here and drew a tangent line, every point you go to would be a different slope. And if you recall, slope is change, rate change, or change, or rate of reaction. So we have what we call an instantaneous rate at this particular point. Kind of make that a little more visible.
And is it that specific point, or is that just every point?
That's right. At a given point, each point has what is generally called, what we call an instantaneous rate. At that particular point, if you took the derivative or something like that. What the next comment should be is, well, what is the average rate of the reaction, or where do we identify the ultimate highest rate of the reaction? And actually, the highest rate is right here, and we call that the average rate. And we'll talk about that in just a second. But the specific points where you notice how the slope of the line is changing. It starts out vertical. The highest slope is right here, which means that's your highest rate. Highest rate of reaction. And at that particular point, then at some point, some time 1, time 2, each one of those points would be a specific instantaneous rate. The central objective is to take instantaneous rates and use them to define what the rate average is, or the overall characteristic of that reaction. That's characteristic of the reaction in that because of the special nature of each of the chemicals reacting, it will have a certain speed, as you might expect. Now, the point of the comments here is to develop what we will be using as units of kinetic units. Okay, since rate is defined as a change in concentration over a change in time, it is appropriate to use some concentration term in the numerator of our units. In chemistry, molarity is the primary concentration term we used, and so it would be a change in molarity as a change in time occurs. Molarity, as you recall, is hopefully, and we'll develop this in more detail, is moles per change in volume, or moles per liter. So we'll see moles, liters, change in over a change in time. Well, this is rearranged in your text and is used quite frequently like this to show moles over liters. Seconds. And that will show up in your textbook in problems, and you'll see them on the worksheets as we go through it, as the primary units for rate of reaction, moles per liter second. Now, moles per liter is still molarity, and some will write change in molarity over change in time. So you'll see a delta M molarity, whatever it is, and change of time from time to time. So you'll be looking for both of them, but both of them mean the same thing. You just have to remember what molarity is. It's moles over liters. Okay, now that's what we should visualize kinetics as in terms of defining its nature. But how do you convert all of this that I've just given you into something that is useful and associated with chemical reactions? Well, rates of reaction depends on what we call rate factors, or proportional to a function of rate factors. If you change one of these factors, you change the speed of the reaction, how fast it goes from start to the equilibrium point. Rate factors can be easily remembered in terms of their complexity as far as all the content of them. Not quite as easy as I'm going to make it here, but you can remember the factors very easily this way. C, A, N, T, C. Can't see. That's an easy enough acronym to deal with. Can't see. This C stands for concentration. So if you change the concentration of one of the components of the reactants, you're going to change you might or might not. If it doesn't change, it's called zero order. But for the most part, you will change the rate or have an effect on the rate of reaction. Surface area. If you try to build a campfire, you probably want to use kindling and small shavings as such to actually start the fire, because it'll start faster instead of one big log to sit down and try to light with a match. The kindling would have a higher surface area and would ignite much faster and react much faster. If you've ever seen somebody do a demonstration where they take baking powder and they'll throw it over a flame, it'll just flame out like that, very fast. So increasing rates of reaction are associated with increasing surface area available to react. Nature of the substances. Nature. This is essentially the study of the whole textbook, really. Okay, a given type of chemical, and you'll see how this works, has a certain rate to it. We're going to work one of our experiments, the third experiment in our list, deals with T-butyl halides. A T-butyl halide has a structure looks like this. One of them is T-butyl chloride, and one of them is T-butyl bromides. So we're changing the components of the compound. And what happens with these, when you put them into water, they change to an alcohol, T-butyl alcohol, and whatever the halogen is will be broken off and hooked up with hydrogen, and you have hydrochloric acid generated, which you can measure with a pH meter, or you get hydrobromic acid from this one right here, and hydrobromic acid. And so what you do is you have a beaker of, say, water, where you actually use water alcohol mix, and you'll drop, say, a 1 ml quantity of the T-butyl chloride in there, and what you'll see happening is the pH as a function of time will fall off like that, and you'll learn to use that to define change in concentration from here over time and get rate for that. Now, you have a world full of molecules, and they're all changes. Now, this is a simple change in halogen attached to it. And you'll find that the rates of the two in terms of savolysis is what this is called. Means it reacts with the solvent. Will have different rates. And those are defined by rate constants, which I'll explain in a minute. Okay? So when we talk about nature, this is many different compounds. And how you change the compound defines how you get a different rate of reaction and how it reacts in the reaction environment. Temperature change. Actually, this is energy content. But temperature fit my acronym a little bit better. Okay, the amount of energy a system has, like if you were mixing A and B, if they're already at a high temperature, they'll have a lot of energy bouncing around, and their kinetic rate would be higher than A and B at a lower temperature. So what we have here is a factor of energy content that we control by increasing and decreasing temperatures. So as we do that, we change the rates of reactions. So we'll see how that works as we go through our study of kinetics also. And finally, catalyst. Catalyst, by book definition, is a chemical which functions to change the rate of reaction, but in itself is not consumed within the reaction. Now, in my definition I just gave you, I did not say faster or slower. A catalyst, you have accelerators and you have retarding agents. An accelerator catalyst speeds the reaction up, of course. And then you have retarding agents which slow reactions down. There's specific reasons for that. For those that would understand it, and we're going to cover it, what you're doing is increasing or decreasing the activation energy level in a given reaction. Activation energy is a hill over which reactions have to pass in order to go to the product side. So the higher the hill, the slower the reaction. And so if you put something in that's going to raise the hill, make a bigger mountain to cross, it's going to be a slower reaction. If you put something in that makes it a lower hill, it's going to be a faster reaction. It's easier to cross the mountains. So things like formulations in antifreeze or coolants for your car function to retard oxidation of the metals which are in your radiator or something. Paint on the wall is in itself a retarding agent. It prevents corrosion of the surface and deterioration, not to mention it offers some aesthetic value. But if you have a patio furniture, iron patio furniture, you probably want it painted to retard the oxidation of the furniture. Okay, now when we measure rates of reaction, the measurement device must be able to identify changes in concentration. So it is a receiver or part of the surroundings of your environment. If you've never been exposed to this idea, in any experimental process or any scientific investigation, you have what we call a system and surroundings. The system in itself is the object of interest, or the chemical reaction in our case. Okay? Take, for example, an acid and a base mixed together, hypothetically, and you have a thermometer in that liquid. You pour the acid and the base into the container, a reaction is going to take place. Acid plus base gives a salt, and a weak electrolyte. Usually the ones they talk about in the book of water being a weak electrolyte. When that reaction occurs, or as it occurs, energy change is associated with it. There are acid-base reactions which are endothermic also, and you have those which are exothermic. I'm using an example of exothermic. So if you have a thermometer in here, it's going to show an increasing temperature as an indicator of how that reaction changes. Okay? So you A and B pour together, open the gates, let it run, temperature goes up. Okay? So you're using a device to measure a change in something. Then you relate that temperature effect change to changing concentrations. And you look in the equation itself, and we'll show you how to do this as we go along, and get an indication of, well, how does the acid concentration change as the reaction proceeds? So over a period of time, we got temperature goes up so far, we can relate that to concentration of the acid change and write a rate. Change in acid concentration over time gives us a rate. And we'll see how this works when we go to the lab, more than right here. But what you have in the detector, this thermometer, is a detector. It's a receiver of what the reaction is doing. And it is part of the surroundings. One thing you may or may not understand about science is you never, ever measure the system effect, the system actually. You always measure the effect of the system on the surroundings. So when this acid-base reaction takes place, comes together, it's sending out heat. And the thermometer is receiving that heat and making a change. So the detector is receiving signals from the reaction. So as it receives the signals from the reaction, it's interpreted by you as a detector, okay, to, well, this is an endothermic reaction or exothermic reaction, and you take the data that you receive and interpret it into what's going on. In essence, we're trying to convert our detector information to concentration terms. So our detector is converted into concentration terms. What kind of detectors do we have in the world? Well, you've got pH meters. Okay, we already showed you a little bit of issue on that. So you'll take a pH electrode and insert it into a beaker and run your reaction and look at the graph, and it'll show a drop or an increase in acid concentration, which is, of course, like I was showing you, the acid concentration out of the Savalas reaction. If you are looking at some other reactions, you might use, well, let's just make a list. Let's see, pH meters. Okay, this is one device you can use to measure the behavior of a reaction as it sends out signals. Okay, okay, UV spectrophotometer. A unique and interesting reaction that is frequently done in the labs is called the bromination of acetone. Very interesting looking type reaction. This is acetone in its basic form. Okay. And if you put bromine in, what will happen is this bromine will go through a mechanistic change and produce brominated, alpha brominated acetone. And it'll give off a little acid. The other half of it will be acetic. Well, what's interesting and what makes us use the UV spectrophotometer is the reactant side is purple. Has a purple color in your solution. And as the bromination takes place, it goes to clear. So as you put this solution into your detector, here's your UV spectrophotometer, and you put your solution, it's called a cuvette, in here, and you run a light beam of UV light through it. It's picked up by the device that tells you how the absorbance of light changes. If you have a lot of purple in your tube right there, okay, you're going to have a lot of absorbance. So you're going to have a high absorbance based on the concentration of bromine in the system. Well, as the reaction proceeds to produce products, what happens to the absorption? It clears up. And so your absorption goes down as a function of time. And so you relate this absorption to concentrations. Okay, that's by UV spectrophotometry. So any device you can use to relate the signals to concentration, fair game in kinetics. So we look at pH meter, okay, and we looked at another one a minute ago, thermometers or thermocouples. Okay, put the thermometer in, or A and B together, temperature goes up or down. You get a graph, and you translate that graph into some kind of concentration per unit time, and say, oh, this goes so fast. Okay? Now, it's a descriptive element that you generate as an observer. You are part of the surroundings. You are not the system. You are just observing and looking at the system. It is the object of interest. And so, what your primary mission in life is, if you're a scientist, is to design, build, and apply devices which receive information from whatever you're interested in looking at. At one point in time in history, I think you can all agree, thermometers didn't exist. So how did people identify hot and cold? Well, stick your finger in, find out if it's hot and cold. You're an observer. You're receiving the signals sent by whatever the reaction is. And over time, somebody comes in, I'm tired of sticking my finger in there, they can come up with the thermometer or thermocouples or whatever, and then graph, and the one we'll use is, we'll draw not only detect the temperature change, but draw the graph for you. And you'll take that and apply it to the technology and come out with a number that says this goes so fast. And so here are three methods that are used frequently, not that one, I'm sorry, down here. 1, 2, 3. 3 methods. But whatever method you use has to be translated, or the signals it receives has to be translated into concentration terms. So it's very important that you have an understanding of how concentration is taken into account when receiving signals from here, from the devices you're using to study kinetics. As a aesthetic trivia point here, Albert Einstein made the comment that in order to understand the universe, you must first learn the language of the universe. What is the language of the universe? Well, it's those signals that are coming in. It's change in temperature, or the change in absorbance, okay, or it's change in pH. And so your job is, once you have a device, it creates some sort of measurement, and you translate that into concentration if you're working with concentration terms. So this is data from your experiment. So it's a real truth that I appreciate from the statement. Anytime you do an experiment, whatever it is, you have to have a box over here, and then you experiment, sending signals to the box, and then you get output from that box, and you calculate whatever You describe what you observe in terms of a story that you want to tell somebody else. In this case, we're trying to talk about rates. There are many stories that can be told in science, but they all start with, sorry about that, they all start with the interpretation of the data that you have. Anybody can collect a number, but what does the number mean is the essence of what we're talking about. Okay, in our outline, if you're wondering what my babble's all about, okay, I just went through, kind of talked to you about the factors and, just kind of an overview, describing rates of reaction and what we use in a general sense to study rates of reaction. Now, this is the meat of the session right here. Everything I've given you up to now is important. I don't minimize that, but what we're about to do is the technology, how to use the rate factors in defining rates of reaction. So, rate laws, proportional to rate factors, or a function of rate factors. Now, we've already mentioned that in order to study the rate of reaction, you have to study one of these factors. You change the factor, you change the rate of reaction. So, rate can be proportional to a function of concentration change. So, you run 1 mole, see what it does, 2 moles, and see what it does. Compare the two rates. Okay, so you're changing concentrations. Rate proportional to function of surface area. Okay, so if you increase the surface area, how does the rate change? Rate proportional to the function of the molecular structure. So you use a T-butyl chloride and compare it with a T-butyl bromide. You change the structure, and it will have an effect. Now, you may do your study in terms of concentration and get a rate from a concentration from the T-butyl chloride and then a rate from T-butyl, and then compare. So you're using combinations of the rate factors. Rate, function. Actually, I use temperature because that's basically what we measure as a byproduct of energy change. And in essence, it's a rate proportional to the function of energy factors, energy content in the system. That is, an A and B before reaction, A and B after reaction. How do you define the difference in energy levels? Well, usually a temperature change. Okay. Rate as a function of addition of a catalyst. Some catalysts are accelerators and some catalysts are retarding agents, as we've already mentioned. We will start our adventure studying kinetics right here with rate as a function of concentration. There are 4 types of problems you'll need to master in this context. 1, rate averaging. Okay. Rate proportional to equation coefficients. Okay. Bigger the number, the faster that component of the reaction is changing. Smaller, the slower it's changing. We'll get there. Rate as a function of experimental observation, experimental rates. There is nothing you can do to define the rate unless you run the experiment. Like you add 1 mole, look at the rate, add 2 moles, look at the rate, but you couldn't have predicted the outcome of the reaction unless you did that. Experimental rate laws. So rate proportional to experimental. This is observation. When you change the concentrations, what happens to the rate? Well, you can't predict it before you run the experiment. And here you have a rate proportional to the decay. Of reactants. How does the reactant concentration change as a function of time? We already showed you the little curve there a moment ago, concentration and time. Typically the reactants will follow that trend. Well, there's a very specific, unique, and classic equation called the decay equation that goes with that. And if you use, say, this might be called a first order decay, and if it goes down sharper like that, that would be a second order decay. Well, the one that goes down with less slope is slower than the one that goes down second order. So we have ways of defining first and second, and there's specific equations associated with those, each line. And if you apply out the signals that come into that equation, and then you can come up with a number of things out of this. The first order rate law you may or may not have seen is very, very classic. That's your first order, and we'll learn how to deal with it and determine, well, what would be the concentration after 2 hours? What would be the concentration after 10 years? Well, this is also used in radioactive decay. All radioactive decay, and you ought to put this on the front burner, if you will. All radioactive decay is first order. All radioactive decay is first order kinetics. And we use this not only for defining first order decay in chemical reactions, but also first order decay in radioactive nuclear reactions and so forth, like that. Okay, let's take them one at a time. Okay, first area is rate averaging. This is derived exclusively, not just exclusively, from the definition of rate of reaction. We'll give you a rate average. If you will get out your handout I gave you, we'll show you how to work a rate average problem. Very straightforward, very easy to do. Okay, we'll look at this first one and its context. Okay, rate, as you already know, is defined as change in concentration, molar concentration especially. Brackets mean molar concentration, if you didn't know that. Change in time. Okay, so what we're looking to do in the problem is calculate a change in concentration over the period of time. Well, if you look at the problem, here is time 1, and there's time 2. Here is concentration 1, concentration 2. So you take the difference, okay, divided by the difference in the times, voila, answer the problem. So that is called rate averaging. And in this particular case, change in concentration would be a 0.00101 mole per liter seconds. See, I'm writing that. Okay. That's a concentration term, sorry. Molar. My bad. Well, getting ahead of myself. Minus 0.00169. And that will be in molarity. Sorry. Okay, that'll be your molarity term. And your time is, of course, 2 seconds minus the first, 8, like that. And so that will be in seconds. Change in concentration over change in time. Actually, second one would be 8, second minus the first. I'm sorry, should be 8 minus 2, my bad. It'll come out negative. What the negative means is the reactants are decreasing in concentration. That's all it means. It doesn't mean it's necessarily slowing down. It just means you are decreasing concentration over the period of time you are studying. So,
How do you know which one to subtract from what? How did you know to do the second?
Second minus the first.
Yeah, how did you know to do
okay, so we get get around 1.33, 1.13, excuse me. 1.133 times 10 to the minus 4 mole per liter per second. That's a capital M on the numerator of the unit. Please note that. That's moles per liter. Let's see, it could be written second. Also, mole, liters minus 1, seconds minus 1. All three of those are the same. Yes.
How did you know to subtract the way you did? Like,
Second minus the first is a, slope. Change in y over change in x. Y2 minus y1 over x2 minus x1. It's just a convention.
Okay.
That's all it is. Okay. Anybody else? Yeah, feel free to ask questions, guys. It's not making sense because I am going kind of fast. Okay. At any rate, that's it. So when you get a problem, it just has a couple of concentrations a couple of times, and it'll be specific in the problem you work. Calculate the average rate of reaction, and like that. Okay, let's see what else we got. Well, I have one in there like that. We are about to get into things called rate laws. I don't know if I want to go there yet or not. I'm not. Let's talk about rate proportional to a function of equation coefficients. Okay. One equation I like to use is the synthesis of ammonia because it has three different coefficients. If we took nitrogen gas and hydrogen gas producing ammonia gas like that, okay? The coefficients would balance the equation there in that context very easily. Interpreting this equation into rate terms is you still use the definition of rate. Change in concentration of change in time. Well, we're going to talk about the rate associated with the N2 gas is change in the concentration of N2 gas, if you will, over the change in time. Let me just put T. That's the rate change of your nitrogen. The others are defined in the same way as far as rate goes. So it'd be rate of hydrogen change would be the change in H2 gas over change in time, and the rate of ammonia production would be change in the concentration of ammonia gas. So it conforms to the definition of rate, change in concentration over change in time, just as we have here. Now the object of problems that you're going to run into with coefficient issues is comparing the rate or determining the rate of one from a known rate of the other. Now please make a note on the sides, this will make sense in a second. We only compare in pairs. Compare in pairs. So if you're given, say, the change in hydrogen over change in time is 0.500 moles per liter per second. That's given. Okay, now you determine the concentration of the other components of the reaction from that. determine change in nitrogen over time and change in ammonium over time, like that. So you're trying to compare one based on the knowledge of another. Okay, now let's scoop down here. To do this, again, you compare in pairs. We will take the known, which is our hydrogen right here, and make it equal to the nitrogen, like this. That's given. And we want that. Now give yourselves a little bit of room in here. You're going to put a number. Over change. Let's do ammonia. We're trying to determine what ammonia is doing. Sir, would you push that door too? I have a way. Hold on. Set the deadbolt. Get out of here. Man, I'm always sitting there. People can't be disturbed. So we equate those two. So we equate those two, and what we want to do is put coefficients in front of them. Okay? So that one is honestly equal to the other. Now, in the nature of the reaction, notice that I'll rewrite the reaction over here. N2 plus 3H2 goes to 2NH3. Notice that hydrogen has a 3 attached to it, and ammonia has a 2 attached to it. The 3, the larger number, means that hydrogen is doing whatever it's doing faster than the one with a lower number. The one with a bigger number is going faster than the one with a lower number, a smaller number. Okay? In essence, we could write, just for descriptive purposes, to illustrate this, change in hydrogen over change in time is actually greater than change in ammonia over change in time. It's going 2 times whatever to 3 times whatever. To make these equal and put them into an equation like I have here, listen, this is it. This is the answer. Swap coefficients. The coefficient for the ammonia is 2. So I'm going to put the 2 over here. The coefficient for the nitrogen is 3, so I'm going to put the 3 right there. You have equated the rates when you do that. One's going faster than the other one based on the coefficient being bigger or smaller. But if you're going to make them equivalent, swap the coefficients and they'll be equivalent in terms of numerical rates, the mathematics. So now you have a simple algebra problem. We are given this, so it's 2 times 0.500 moles per liter is equal to 3 times the change in ammonia over change in time. And if we're interested in the rate of ammonia, all we do is solve that equation for the ammonia. Okay. 2/3 of 0.500 molar per second is answer. So this is now the absolute defined rate based on coefficient numbers. Problems will come to you just as exact. You'll be given an equation, one of the components, and you calculate the other one, or whatever's being asked. Finish this one. This gives us ammonia, but what about the hydrogen? Well, I mean, nitrogen is one. You could either use either one of them now because you got 2 data points that you can use. We'll stay with the hydrogen. So you set that equal to your change in hydrogen over change in time, which has been determined by whatever method or is that somebody else? And we look at the coefficients here and the equation. So I see the 3 is associated with hydrogen, so I want a 3 over here. And then I want a 1 over here. Okay? So actually hydrogen is doing whatever it's doing 3 times faster than whatever nitrogen's doing. And that's a logic in the equation. Hydrogen is going away 3 times faster than the nitrogen, based on the nature of the equation right there. And so all I have to do is solve for the concentration over time for nitrogen, which would be 1/3 of 0.500 mole per liter. Which is 0.167 molar per liter. I'm putting all this on. Mole per liter. So, just a second. So, what do? We've got an equation. You'll be given one of the rates. All you got to do, and asked to calculate one of the component rates. You set them equal, swap coefficients. Substitute the data. Voila, you got your answer. Just a second. Got a question in the back there. Back up here. At the full screen. Okay. Now, experimental rate laws. This is kind of labor intensive, but it's doable. Come on. Okay, so this is the third type of problem you'll have to deal with in kinetics, experimental rate laws. Now I like to use this equation a lot. I'm going to reuse the nitrogen gas plus 3 because it has different coefficient. Gas goes to 2NH3 gas. Okay, the problems that deal with this and that you'll work on in terms of a given equation that you're interested in solving information on. We'll start by asking you, what is the rate law? Like that. You write the empirical rate law and solve for the variables. Now, what do I mean by empirical? Empirical rate law is in terms of variables associated with the behavior of the reaction. It's always written, the empirical rate law is always proportional to reactants. I should have said just simply reactants. Proportional to reactant concentrations. So you disregard the product side altogether. You have absolutely no interest in the product side when it comes to writing an equation. However, you are at liberty to use the evolution of something in the product side if your detector needs it, and then translate it to a reactant component. For example, we're using the T-butyl bromide. It's going to make an acid. We're going to use pH meter and measure the acid rate generation. But we'll interpret that as equal to the rate of disappearance of the halide. We'll see this several times. But anyway, empirical rate law, regardless of the equation you have, is written in terms of the reactants. So given an equation, of course, we recognize the reactants. We write the empirical rate law as rate equals, that's how you start it, lowercase k times the concentration, molar concentrations, of the components of the reactant side. Now, even though it has a 3 in front of it, you don't put that 3 inside the brackets. You're just looking at individual concentration, molar concentrations, raised to an exponential value. Okay? The K in this issue is called the rate constant. And for all practical purposes, people use this as, since it's directly proportional, okay, as a measure of the speed of the reaction. It's the speedometer of the reaction. So we're going to do an experiment, and we're going to come out with a rate constant value, whatever it is, for your savolysis of T-butyl chloride. You're going to compare it to the rate constant for T-butyl bromide. You compare the two, and then translate that into some chemistry. But that's called the rate constant. It's the speed of reaction, moles per liter per second or whatever. It's a proportionality constant. And sometimes comes up with some weird units on that. The X and the Y's are known as order of reaction. Order of reaction reflects or identifies behavior, rate behavior of the component of the reaction. Case 1, as a function of time and concentration, we'll say we're looking at nitrogen, change in nitrogen concentration. Whatever. If we apply 1 mole of nitrogen to the reaction, disregarding hydrogen, then turn around and run a second experiment and double it, we look and see if it produces a change in rate. So if we see that concentration, I should have used rate. I'm sorry, change this to rate. Make it easier. Right there. We're looking for a change in rate when we change the concentration of a component. So we ask ourselves what happens to the rate at that component if we change that. And you'll see this in the data and the problems. If you look down there at the bottom of the first page, you'll see they use a bunch of concentrations, and then they show some rates over here, like that. We'll work that one in a minute. Okay, if you change concentration of the component and you don't get a change, it's called a zero-order reaction, and the exponent becomes 0. And you would see a trend like this. So your rate as a function, well, let's change this one too. I'm sorry, I'm misfiring. This should be concentration down here. So you change concentration and see what the rate does. If the rate doesn't change, it's called a zero-order reaction. Zero-order reaction. Different reactions. Okay? And you identify one of the components you want to study. And so you change that one. You look at the rate at concentration 1, rate at concentration 2, and you notice that it doubles. And then you triple concentration, you notice it triples. Well, the rate trend would then be linear. If you see that happening, you have a first order reaction. Double concentration, double rate, triple concentration, triple rate is an asymptotic linear curve. If you study a third reaction, whatever it might be, and you take a component, a single component, and we call it the reference reaction rate. Reference rate would be the first one. And then you double that concentration, and it goes up 4 times. And then 9 times, 12, 15 times. It goes up exponentially as you study it in terms of the rates versus changing concentration. They jump real fast in rate. This is multiple, or let's just call that the second order. So you would use, if this was a first order reaction, X would equal 1. If hydrogen is determined to be a second order reaction based on the data you look, it would be a 2. If you had another component or a different reaction and it was a third order, it would be a 3 exponent. and those define the rate trends. These are rate trends. And so that's one of the things you're looking for in the behavior of a given reaction. A reaction has, let me be sure we show you something here. This has a coefficient of 1, this has a coefficient of 3. In the kinetic region, remember what we talked about in the kinetic region versus the, when you're studying something in the kinetic region, you cannot assume the coefficient to be that exponent. You can assume the coefficient to be the exponent in the equilibrium region because the concentrations aren't changing. But the only way you can determine the order of reaction or that exponent is by experiment. It might come out 1 first order. It might come out second order and match the equation. But that's only circumstantial. In the kinetic region, you have to do an experiment and observe the outcome to determine the order of reaction. Okay? And so we'll do that. Determining rate law of a reaction. We're going to use a hypothetical reaction. A goes to products. What's the A going to do as a function of time in terms of concentration? It's going to drop off. All right. To write the rate law, remember what I said, the first question about rate is going to be, what is the empirical rate law? And then you fill it in for K's and X's and Y's or whatever you assign as the, I can use A, B for exponents if you want to. The rate law for this equation is K times A raised to the X power. That's the empirical rate law for that equation. Everybody good with it? All equations. If this had had AB, let me give you a contrast. A plus B goes to products. Rate is equal to K times A raised to the X power, B raised to the Y power. It's always in terms of the reactants. Whatever you have in the problem given, it's always in terms of that reactant side. Is that okay, everybody? Very simple, nothing more, nothing less when dealing with experimental rate laws. Okay, now we want to come down and use this. And what trend should you see if X is equal to 0 for a first order? We're going to let X equal 0 for rate equals K on to A, the power up here. So that's going to be 0 order. Any number raised to 0 is constant. Exactly. So this would become 1, a constant. And so the outcome is constant. So a first order trend, as you change concentration, is linear. I mean, horizontal, 0 slope. Sure it's linear. Okay? It means that you are having a constant rate. Now what you did is you changed the rate, concentration. You took 1 mole. It had 1 mole per liter per second. Then you doubled the concentration. It still had 1 mole per liter per second. Triple the concentration, still had 1 mole per liter per second. The rate stayed the same for every concentration in the world you use. So when you plot how does the rate change when you change the concentration, it comes out as a flat line. That's called a 0 order reaction, and your X would be equal to 0. What?
So, did you name it first order because it's the first?
I didn't give it first order. I said that's zero order. What did I? Oh.
It said first order, I'm sorry.
Senior moment. Okay. Zero order. My bad. Okay. My bad. Okay. See if I can get improved some. Okay. Now, what you want to do is let x equal 1 now, and play with the trend change. Okay. So let's let x equal 1 for the same reaction to the first power. So what would rate be? So we'll say, let's let our concentration A be A, 2A, 3A, so forth. We're starting out, the first one, the first A concentration is what I call the reference, because you're comparing everything else to that. Okay, so by substituting this concentration, it's a number, into that equation, we have rate 1, let me do it this way, rate 1 will be K times A, rate 2 will be K times 2A, rate 3 will be K times 3A, which translates, of course, to 2KA, 3KA, and so forth. All right? So if I double concentration, I doubled my rate. Ka is this rate, reference rate. If I triple concentration, it goes 3 times. If I go to 4A, the equation will increase rate by 4 times. When you see that changing trend in rates, you have to do it experimentally. You assign a first order, and that will be the linear trend. So you would put a 1 into the empirical rate law. So you'll get data that is asking you to define what that x is. And you look and see if the data changes, the certain way data changes. And then you make a decision on whether it's 0, 1, 2, or 3. Let's do it. To make life easy for you, you will not see anything higher than a second order reaction in your exams. So it'll be pretty straightforward. Okay, let's let x now be a 2 for our empirical rate law. Okay, like that. And we will look at the trend that is generated as we do the same thing with concentrations. Double it, triple it, quadruple it. So if we have, I'm going to make a little table here. A, 2A, 3A, 4A, and then we want to look at a rate. So the rate is equal to Ka raised to the second power. So we have K times A squared for that one. Then we have K times 2A squared for that one. We have K times 3A squared for that one, and K times 4A squared for that one. So we just simply took the empirical rate law and applied changing concentrations. The first one, remember, is the reference. You have to have something to compare to. So we call the first one a reference. And so this comes out as Ka squared. And this comes out 4Ka squared. And this one comes out 9Ka squared and 16Ka squared. So if you increase the concentration by 4 times and ran the reaction, you would see a 16 times increase in rate as compared to the reference. The reference rate is always the first one out of the box. I got 2 minutes to, well, we'll take an extra minute. All right, here's how the problems come together in here. If you'll get this sheet, and look down here at the bottom. Okay, if I can get on. Everybody see that? Well, I'm sure you got that one in front. Okay, in working rate law problems, here's the underlying theme. Listen to me carefully. Hold one constant, okay? Don't change it, and then vary the other one, see what happens. Hold one constant and vary the other one. Okay, for example, we're going to try to find the rate law for this, right here. Okay, so rate, empirically, is K on to NO as a gas and Cl2 as a gas raised to X, Y power. Your job is to find out what X, Y, and K are in that problem. So we want to hold one or the other constant and then vary the others. Here, look here as the data is given you. Here and here. We don't change the concentration. We hold it constant. But we did what to the NO? We doubled it in here. Then you look at what happens to the rate. You take 4 point, most of you can probably just visualize it, 0.468 divided by 0.117 gives me 4. Okay? It went up 4 times. Increase by a 2 times increase in concentration. A double concentration, but the rate went up 4 times. What is the conclusion? Second order. Because we already looked at that earlier. If you double the concentration and the rate goes from 1 reference to 4 times jump, then you draw your conclusion that the, make sure I'm on the right one. Yeah. We did NO, so that is now a 2 in there. That's all you do. Now we want to hold the other component constant and vary this one. Here's a constant. Now this data is not in sequence for any particular reason. You have data all over the place. You just hunt for constants and variance. See, now in this second trial, we hold this one constant right here, and we double this 2x, and we look over here and see what this one does. In this case, that looks like a 2x increase in rate. So if we double concentration and we have a double rate, our order of reaction is first order. And so we assign a 1 to that. And so now our rate equation becomes K NO concentration squared Cl2 to the first power. Of course, you don't have to put it up there.
Wait,
2 and 1.
Why is Y 1? Why is Y equal?
Okay. Hold one constant and look at the trend and change in rates. Hold a constant, look at the rate trend. Okay, the equation here, so what we're doing in this second set of experiments is we're holding this one constant and seeing how the rates change if we double the concentration. Well, we went from 1.54, which is your reference, to 2.107. That's twice, 2 times. So it increased twice. Our conclusion is that's first order. You double concentration, you double rate, it's first order. Because that is the empirical definition of a first order. Here's what we're showing. I took my component and I got my reference. This is my reference. Then I double concentration and it doubled. If I had a 3 times increase with a 3 times change in concentration, I'd still call it a first order. Is that what you're asking?
Yeah.
Okay. And so what you do is you assign the 1 to it. So it's a matter of experimental. There's no mathematical calculation you're doing. You're doing experiment and observation of outcome, input and outcome. You interpret the outcome, that is a signal what the reaction's telling you, as a first order, double concentration, double rate. Second order, double concentration, quadruple rate. So it's a matter of, this is behavior, indicators of the behavior of the reaction. What's the reaction doing? Now the last thing you have to do is determine the K value in here. So you solve this for K to equal rate over NO concentration squared Cl2 concentration raised to the first power. And all you have to do is pick any row, because constant's a constant for any row that you choose. That's why K is K, constant, it will not change. So if I chose the first row in here, I can calculate K for row 1. And then in row 1, the rate is 0.117 mole per liter per second, right there. Concentration of nitrous oxide is 0.10, but we have to square that. And the concentration of Cl2 is also 0.10, but it's to the first power. And so that would come out molar cubed. And see this, molar squared, molar cubed. Anybody on that? Okay, so we can come down here in molars per second times 1 over molar cubed, and our final units would be seconds minus 1 molar to the minus 2. These will be the units when we finish pulling this thing together. Okay? This is mole per liter per second. This is molar squared plus 1 more molar, and we got molar cubed, and I just went through the algebra right there. Hope that made sense. If not, we'll do some more. That's molar over seconds from the other one. But anyway, that comes out 0.117 divided by 0.1 divided by 0.1, and that's equal to, I get 117. I like to put molar first, just personal. You don't have to, but there's your K value. Now, as a proportionality factor, weird units are illegal because they're dependent on the equation that is given. So now you can write the numerical rate law for the equation, and of course the answer is the answer to the problem. Rate equals 117 molar minus 2 second minus 1 NO squared Cl2 to the first power. So with that, you can use whatever combination of nitrous oxide and chlorine. Plug in the observed rates and, for the given concentrations you're using. Now just plug in the concentrations that you want to use for any combination, and you'll get a rate. It's an equation that is specific for the given equation. Now there's one other comment here on this, and then we'll close and talk about lab. Okay, the overall order of reaction. This is the order of reaction for nitrous oxide. This is the order of reaction 1 for chlorine. But what's the equation overall order of reaction? It's the sum of the exponent values, which is simply 2 plus 1, 3. The overall rate, the overall order of that reaction is a third order reaction. Very steep slope when both of them are acting together.